Okay. As opposed to that, do you see at the same temperature, in this particular case, you have a phase transition from solid to liquid? Yes? So at the same temperature, you're stuck at T2, you had a huge change in delta H. It looks like a step function. Yes? This change is because of phase transition. So this particular one, when you went from solid to liquid, is it positive or negative? Positive, because you went from solid to liquid. You can see that delta H went up, so it makes sense that it is positive. Similarly, you went within a liquid, so I will take the case of ice, okay? Let's say I had ice at minus 5 degrees C. I first need to, if I want to get to vapor at 300 degrees C, I first need to go from 5 degrees C to 0 degrees C. Agree? And then I have a transition to liquid, and from here, this temperature should be 100 degrees C, right? At 1 atmosphere. And then this then would become what? The heat of vaporization for water, right? And then I would have another step to get to 300 degrees. Is that clear? Yes? Do you also see then, is when you went from liquid to vapor, is this delta H positive or negative? Positive? Yes? Because your delta H actually went up. Now let's go opposite. Let's start at 300 degrees C vapor and go down to minus 5 degrees ice. What happens? Do you see that I first lose some heat to come down to 100 degrees? Then I lose a significant amount of heat for the transition. I lose some more heat here. Yes? And then, okay, maybe use a different colored pen here. And then, do you see that I lose a lot of heat here as well? So does it make sense that we said that the delta H is negative in these cases? Yes? So when we went from vapor to liquid, delta H was negative. When we went for liquid to solid, delta H was negative, right? So pictorially also, it makes sense. Yes? I am bad at memorizing, so images make more sense to me. Whichever way works for you, use that. But just remember this sign. Okay? All right. Then the last part of this, and we still have enough time, so we are good, is how do I use this concept to then solve problems where you have phase transitions? My point that I want to hone in, and I think at the expense of repeating myself 100 times, I would like you to recognize that the most important step is actually identifying the path, right? Because people will just tell you that you had this table where you had a phase transition, or they won't even tell you phase transition, right? They will say hexane was at 25 degrees C and is now at 300 degrees C. Hexane can exist as a liquid at 25 degrees and exist as actually only as a vapor at 300. So they never even told you where the phase change was. What does that mean? What does that mean? You have to know it or find it and create your own path to get from 25 to 300 for hexane. Is that clear? The second thing I want you to think about is, every time you think about the path, also think about identifying which part is my sensible heat and which part is my phase change latent heat. Okay? So anytime I'm going through a temperature change in the single phase, it's sensible heat. Anytime I'm having a phase transition, it's latent heat. All right? The third thing I want to think about is make sure that that temperature, that path that you draw, passes through whatever latent enthalpies you can find on the table. Do not think of temperatures that are not on the table, because that becomes miserable, right? Because then you'll end up having to calculate things where you don't need. And also, the most important part is don't leave any gaps in your path, because then you have a problem. All right. And then lastly, make sure you know what your limits are, right? If you don't know your limits for the integrals, then that becomes a problem. But once you know your limits, don't worry too much about the sign. For sensible heat, as long as you have your limits correctly identified, the integral just works out. It's only for the latent heat that you have to watch the sign. But that we already established, latent heat, how we work through the signs. Okay, so with this, ready for a calculation? Yes? Okay, so we will use steam tables where possible. If steam tables are not available, we will always have to think about a path to make our calculations. So here's an example. I realize we have 5 minutes, but we can at least set up the path. So what this example problem is telling me is that I have 100 gram moles per hour of liquid hexane, which is at 25 degrees centigrade and 7 bar. It is vaporized and heated to 300 degrees centigrade. Did you catch a few important words here? Exactly, right? So another word is, I started out liquid. I have been vaporized. Well, I have not been vaporized, but hexane has been vaporized, right? And all of this is happening at constant pressure. So that also helps us. Neglecting the effect of pressure on enthalpy, estimate the rate at which heat must be supplied. So what is the first thing we need to do here? Set up a path. Before that, can I just also suggest, let's always do energy balance. I am going to write out my energy balance because I need to find out that whether I even need to calculate H or not. Chances are I do, but still. Okay, do I have EP and EK in this problem? Do I have any shaft work? No. So that means that when I'm asked to calculate heat, I do have to calculate the enthalpy. So I did have to set up a path. Yes? So now let's set up that path. What do you think should I do first to set up the path? What's that? Initial and final states. Okay, so what are my initial and final states? My initial state is 25 degrees C, I believe, and liquid, yes? And my final state is what? 300 degrees C and vapor, agreed? Okay, that means what all do I worry about in my path? Exactly, somewhere vaporization happened. How do I know where vaporization happened? Use the table. Can I use steam table? Because it's not water. So I go back to my list of tables and try to hunt for which table will I go to though? Okay. So the first thing I want to show you, luckily, as you start shuffling through all these tables, do you see the very first table has delta HM and delta HV? Saved by the bell. right? Almost, I still have 1 minute. Okay, so that means that I better go look for that delta H vaporization for N-hexane. Okay, it turns out for N-hexane, the temperature where vaporization happens is at 69 degrees C. So now this is where delta H